So the magic, in a sense, of qubits is that it allows you to do parallel computing, but with one device.
In previous videos, we talked about what quantum computing is and how it works at a high level. Now we're going to dig a bit deeper and explain ion trapping, a quantum computing method with unique practical advantages. We'll also cover some of the key differences among quantum computers and why they matter. With its unparalleled computation ability, quantum computing is energizing businesses and technologists worldwide. But there's more than one way to harness quantum physics for mind-boggling calculations, and they are far from equal. Many quantum hardware providers use synthetic atoms for the qubits, like in superconducting circuits or quantum dots in semiconductors. When using ion traps, the qubits are made of naturally occurring quantum systems, individual atoms.
We don't start from fabricated qubits. Our qubits are atoms that are given to us by nature, and each and every atom that we use as qubits are exactly identical.
As IonQ's name suggests, ions, in other words, charged atoms, are the heart of our computers. These are our qubits, the quantum building blocks for computation. And an ion trap, you guessed it right, is exactly what it sounds like, a device for capturing ions. Here's how it works. We start by selecting elements that have properties that make them uniquely suited for quantum computing. First, lasers zap the electrons to transform the neutral atom into an ion with a positive electric charge.
These atoms are in a pretty exotic environment. They're electromagnetically confined. They're levitated, in fact, above a set of electrodes. Now we put them on a chip. The chip is inside of a vacuum chamber. And that's because you need extreme isolation.
On the chip, the ions form ion chains that hover above the device. In other words, they create a chain of qubits. Voila! We've trapped the ions, and now the system can manipulate them. A set of highly precise lasers and optical systems inspect and influence each individual ion in the chain, forming a subatomic light-powered computing system. Then, the computer uses our quantum operating system to put the ions to work based on the quantum circuit being executed. It resets the value of each qubit and applies quantum logic gates that create entanglements. Then, the operating system utilizes these quantum logic gates to manipulate the information and implement a quantum algorithm. Finally, it reads the values of qubits to extract the answer to the algorithm. The hardware can even physically shuttle individual atoms across space to expand the size of the system so it can handle more complex calculations. But how do we know ion trapping is the best way to run a quantum computer? It's tempting to search for a simple performance metric to compare quantum computers, like the number of qubits. But counting qubits alone, without understanding their characteristics, is like counting bolts in an engine as a metric for evaluating a car. It's not an accurate representation of quality or utility. A better benchmark is fidelity, a measure of how close the real-world outcome of the process is to the theoretical outcome. And this is where ion trapping is particularly useful. Quantum computers are based on probability and non-deterministic values. Due to imperfections in control and interactions with the environment, qubits are expected to have limited fidelity. It can be a bit confusing to think that the most advanced computing machines might have limited accuracy. But that's just how the technology works. And when systems are designed correctly, quantum computers still produce unmatched results. One of the differences among quantum computers is how quickly this inaccuracy becomes an obstacle. For example, even if a quantum computer can achieve fidelity of 96% accuracy in entangling 2 qubits, the remaining 4% error rate multiplies and compounds as you entangle more qubits. With only 10 entangled gate operations, our 4% error rate translates to only 66% accuracy. Add 5 additional gate operations, and the system performs slightly better than a coin toss with 54% accuracy. Fortunately, physicists and engineers have figured out ways to reduce inevitable errors. When you're comparing quantum computers, be sure to look at error rates and solutions for error reduction. As of 2022, when entangling two qubits using IonQ's technology, the achieved average fidelity is already well above 99.5%, with a roadmap that plans to increase it up to and beyond 99.9% in the next several years. Another way to compare the quality of qubits is quantum coherence, a measurement of how long a qubit retains its information. Due to unpredictable interactions between quantum systems and the environment, over time, a qubit falls apart or collapses and it loses its coherence. They can't be formed, entangled, and used in calculations forever. Its data is lost and it needs to be recreated. In some quantum systems, especially those based on superconducting circuits with artificial atoms, this coherence duration is measured in mere milliseconds. But natural ion qubits are very durable and are protected from the environment because they are floating in vacuum space, so they stay coherent for much longer than the entire duration of a typical computation. Now that we have qubits with high fidelity and long coherence time, we need to make sure that they can be entangled. Remember, entanglement is a phenomenon in which the quantum states of two or more objects are correlated, even when not passing information between each other. This enables quantum computers to perform logical operations and find solutions to complex problems. Unfortunately, that connection between qubits cannot be taken for granted. The layout that determines the connection between qubits can introduce significant limitations. We call this the computer's connectivity. It often forces some qubits to be used only with a small set of other qubits directly, instead of all of them. It's the equivalent of saying that people in an organization can only email some of the other people and rely on them to forward it to the intended recipient. Better than nothing, but highly limiting. IonQ's baseline architecture forms an all-to-all connectivity. This means that any qubit in the ion chain can be entangled and logically processed with any other qubit in the same chain and with adjacent quantum chains. To sum it up, quantum computing is an emerging industry, and its key benchmarks haven't been standardized yet. As of 2022, there are no generally accepted objective criteria for comparing computational power or even the utility of quantum computers. IonQ is also working to define the benchmarks and is collaborating with a consortium of quantum computing leaders to work toward a consensus that would help companies evaluate the right solution for their specific needs. This approach for measuring the performance of application-oriented benchmarks is based on real-world algorithms that solve real-world problems, and that's the best way to know which quantum computer is right for you. In the meantime, here's what you should consider. The coherence time of qubits can cause limitations in quantum implementations. The fidelities of various qubit operations can compound and cause calculations to be highly inaccurate. The number of available qubits for calculations can limit what kind of algorithms can be implemented, and the connectivity limitations between qubits can reduce the computer's efficiency and accuracy.
So the future of quantum computers will need users, not only as customers, but as those who will invent things to do with quantum computers.
It's a lot to process. If you have questions or feedback, please reach out to the IonQ team.